11:57 at night, March 12, 1928, and a wall of water more than 100 feet high is roaring down the San Francisco Canyon at the speed of a freight train with no driver. The air tastes of wet limestone and diesel smoke. Somewhere below, orange groves are still warm from the afternoon sun. The moon lights the ridge just enough to see the shape of it. A concrete dam, roughly 700 feet across, its curved face suddenly splitting like a jaw opening. Not slowly. Not with warning groans that give people time to run, in seconds. Camera close, if there were one, a fraction line racing up gray concrete, water forcing itself sideways through a crack no wider than a man's finger, then a section the size of a house simply leaving its place. 12 billion gallons let go at once. Down in the valley, in beds, in kitchens, in a school built for the children of dam workers, nobody yet knows the shape of the night that has just started. Why does a structure engineered by one of the most respected watermen in America fail in under 3 minutes? And why, a century later, will the answer to that question force engineers to go back and study concrete poured by the Romans 2,000 years earlier? To understand that, we have to step back. Not 3 days before the collapse, but roughly 6 hours. At around 6 in the evening on March 12, a dam keeper named Tony Harnischfeger walks the base of the St. Francis Dam and sees something he does not like. Water, muddy and unusual, seeping from the west abutment where the concrete meets the canyon wall. He telephones his superior, the chief engineer of the Los Angeles Bureau of Water Works and Supply, a self-taught Irish-born hydraulic engineer named William Mulholland, the same man whose aqueduct had already turned a desert city into a metropolis. Mulholland drives out that afternoon with his assistant. He examines the seepage, the color of the water, the ground around the leak. Historical accounts, drawn from testimony given at the inquest days later, record that Mulholland judged the leak typical for a new dam settling into its foundation. Nothing unusual, nothing worth emptying the reservoir over. He returns to Los Angeles. Nobody sounds an alarm. By midnight, the dam is gone. To understand why that decision mattered, and why concrete itself was already carrying a hidden weakness nobody in 1928 fully understood, we have to go back much further than that afternoon. Back almost 2,000 years, to a harbor town near Naples called Puteoli, and a builder's manual written by a Roman named Vitruvius sometime in the 1st century BC. Vitruvius describes, in his treatise, the Architectura, a mixture used by Roman builders, lime, seawater, and a reddish-gray volcanic ash quarried from the hills around Pozzuoli. Mixed with chunks of rock and lowered into wooden forms in the sea itself, this material did something that should have been impossible for the technology of the age. It hardened underwater, and it kept hardening for centuries. The smell of that mixture, if you had stood beside a Roman work crew loading barges with volcanic ash near the Bay of Naples, would have been sulfurous and mineral, the ash still faintly warm from geothermal vents nearby. The men handling it wore no gloves. The lime burned their skin if left too long. And yet, what they built with it, harbor moles at Baiae, the piers at Portus, the enormous unsupported dome of the Pantheon in Rome, completed under the Emperor Hadrian around 128 AD, still stands. The Pantheon's dome remains to this day the largest unreinforced concrete dome on Earth. Here is the first quiet fact worth sitting with. Nobody fully knew, until modern chemistry caught up, exactly why that Roman recipe worked so well for so long. For nearly 2,000 years, it was simply believed, accurately, as it turns out, that Roman concrete got stronger with age, while the concrete of the modern industrial world, the concrete poured into St. Francis Dam in 1926, tends to weaken. That contrast is the shape of the story, but we are getting ahead of it. After Rome fell, the knowledge of pozzolanic concrete did not vanish overnight, but it faded. Records show that through the medieval centuries in much of Europe, builders returned to stone, brick, and timber. The particular alchemy of volcanic ash and lime became, in practice, a lost art. Not because anyone destroyed the manuscripts, but because the supply chains, the skilled masons, and the imperial ambition needed to build on that scale simply disappeared along with the empire that had organized them. It would take roughly 17 centuries for something resembling concrete to return to everyday construction, and when it did, it arrived not from a rediscovered Roman secret, but from a bricklayer's kiln in the north of England. In 1824, a Leeds builder named Joseph Aspdin patented a cement he called Portland, because he believed the hardened gray material resembled the prized limestone quarried on the Isle of Portland. Aspdin's process burned limestone and clay together at high heat, then ground the result into a fine powder. Mixed with water, sand, and gravel, it produced something new, a manufactured, standardized, endlessly reproducible building material that did not depend on any one volcano, any one quarry of ash. This is the moment concrete stopped being original craft and became an industrial commodity, something a nation could pour by the ton, ship by rail, mix on any construction site in the world with the same reliable result. Within decades, Portland cement was pouring the foundations of sewer systems in Paris, factory floors in Manchester, and, eventually, the caissons that anchored the towers of the Brooklyn Bridge sunk into the East River bedrock in the 1870s under compressed air, workers laboring in conditions so extreme that dozens suffered what came to be called caisson disease, what we now know as decompression sickness. By the early 20th century, concrete had become the material of ambition itself. It built dams that tamed rivers, skyscraper foundations that let cities climb, and highways that stitched continents together. It promised permanence at a scale stonemasons could never have imagined, all for a fraction of the cost, poured wet and shaped by nothing more than a wooden form and a schedule. And it was exactly that confidence, in a material barely a century old, still being learned even as it was being trusted with human lives, that filled the reservoir behind the St. Francis Dam. The dam had been built quickly, between 1924 and 1926, under Mulholland's direct supervision, as part of the same Los Angeles water system that had already made him a hero of the American West for delivering the aqueduct that let the desert city grow. Records from the subsequent investigation note that the dam's height was raised twice during construction without widening its base to match, a design choice that, decades later, engineers would flag as a critical weakness in how the structure distributed its own weight. There was also the ground itself. The west abutment of the dam sat against a formation of ancient landslide material, rock that had already failed once, geologically speaking, thousands of years before any human poured a bucket of cement into that canyon. Nobody performed the kind of deep geological survey on that site that would become standard practice for dam construction only after this disaster forced the profession to change. So, the first rung of escalation is quiet and administrative. A dam built fast, on ground not fully understood, raised taller than originally planned. The second rung is human and stubborn. The afternoon visit, the muddy seepage, the veteran engineer's judgment that it was nothing. A judgment made by a man who had spent decades being right about water, and who, on this one afternoon, was catastrophically not. The third rung is mechanical, and it happens in the dark. Sometime before midnight, the west abutment gives way completely. 12 billion gallons, enough water to cover a city block more than 8,000 feet deep, surged down San Francisco Canyon and into the Santa Clara River Valley, sweeping through the town of Santa Paula and toward the Pacific 54 miles away. Investigators later placed the death toll near 431, though the true number is still debated, since migrant farm worker camps in the flood path were not always fully counted in official records. Entire families, entire bunkhouses, vanished in the mud before dawn. Mulholland, at the inquest that followed, reportedly said he envied the dead, that he wished it had been him. He never held public office again. His career, built over 40 years, ended in 3 minutes of concrete failure he had personally inspected hours earlier and judged safe. For decades, the standard explanation for the collapse rested almost entirely on that afternoon decision and that unstable hillside. Case closed, tragedy filed, next generation of engineers taught to survey foundations more carefully. And that would be where this story ends, if not for a piece of research published nearly 90 years later that quietly reframed everything that came before it. In 2017, a geologist named Murray Jackson, working with a team that included researchers from the University of Utah and collaborators studying ancient harbor structures through what became known as the Romacons Drilling Project, published findings in the journal American Mineralogist examining concrete cores drilled from Roman maritime structures near Baiae and Portus, concrete that had been sitting in seawater for roughly 2,000 years. What they found was not simply that Roman concrete had survived. It was that seawater, flowing through microscopic cracks in the material, was reacting with a rare mineral called aluminous tobermorite, forming inside pockets of lime left in the mix. That reaction did not weaken the structure over time. It reinforced it. The cracks, instead of spreading, were slowly filling and strengthening with new mineral growth. The concrete was, in a very literal sense, healing itself as seawater worked through it, decade after decade, century after century. Modern Portland cement, the very material poured into the St. Francis Dam and into nearly every concrete structure built after 1824, does the opposite. It is engineered for rapid strength and standardized performance, but it lacks that particular self-repairing chemistry. Worse, modern concrete is almost always reinforced internally with steel bars for tensile strength, and when water finds its way through hairline cracks, as it eventually does in nearly every structure, it does not heal the concrete. It rusts the steel inside it. Rusting steel expands. Expanding steel cracks the concrete further from the inside out, in a slow, invisible process engineers call spalling, one of the leading causes of infrastructure failure across the modern world. So here is the quiet reversal sitting underneath the entire story. The material that failed catastrophically in one night in 1928 was, in a real chemical sense, less durable at its core than a recipe developed by Roman engineers who had no periodic table, no concept of aluminous tobermorite, working from instinct, observation, and volcanic ash quarried a short cart ride from the sea. The Pantheon's dome, poured under Hadrian, has stood through earthquakes, empires, and 18 centuries of Roman winters without a single structural repair to its concrete shell. Francis Dam, poured under the best engineering knowledge 1920s America could offer, failed in under 3 minutes, less than 2 years after the last bucket was set. That is not a story about ancient people being smarter than modern engineers. It is a story about what gets carried forward through history and what gets lost, and how easily confidence in a new material can outrun our actual understanding of it. The aftermath of the St. Francis Dam collapse reshaped American engineering practice permanently. California established some of the first state-level dam safety oversight laws in the country directly in response to the disaster. Geological surveys of foundation rock became mandatory before major dam construction, a practice that, decades later, helped inform the extraordinary caution poured, quite literally, into the construction of the Hoover Dam, begun in 1931, only a few years after St. Francis fell. Hoover Dam's concrete was placed in small blocks with embedded cooling pipes to control the heat of curing, an engineering solution to a separate problem, thermal cracking, though the broader caution about dam site geology owed much to lessons from St. Francis. And in recent years, the Roman discovery has done something else. It has sent modern researchers back to the drawing board, not out of nostalgia, but out of necessity. At Delft University of Technology in the Netherlands, a microbiologist named Hendrik Jonkers has spent years developing what is sometimes called self-healing concrete, embedding dormant limestone, producing bacteria and calcium lactate directly into the concrete mix. When water enters a crack, the bacteria activate, consuming the calcium lactate, and secrete limestone that seals the gap from within. A modern biological echo of what Roman seawater and volcanic ash were doing by chemical accident 2,000 years earlier. It is a strange kind of circle. The material that quietly built the modern world, sidewalks under our feet, foundations under our homes, bridges under our commutes, the walls of hospitals and schools and airports, turns out to still be, in some real chemical sense, an unfinished experiment. We solved the problem of making concrete cheap, fast, and everywhere. We are only now catching up to the problem the Romans apparently solved by accident, making it last. That matters to more than historians. Right now, in the United States, the American Society of Civil Engineers has repeatedly graded the nation's aging bridges, dams, and roadways with mediocre marks, citing thousands of structures built decades ago from concrete, that is, at this very moment, undergoing the slow internal rusting that Roman concrete never had to endure. Across Europe, aging post-war concrete infrastructure faces the same quiet countdown. Every parking garage, every overpass, every apartment tower poured after 1824 is, in a sense, running on borrowed time in a way the Pantheon simply is not. And globally, the scale of this material is almost impossible to picture. Cement production worldwide now exceeds 4 billion tons a year, making concrete, sand, gravel, water, and cement mixed together, one of the most widely used manufactured materials on the planet, ahead of steel, plastic, or wood by volume. Every year, humanity pours billions of tons of concrete, by some industry estimates enough to blanket vast stretches of land, though such comparisons vary widely. Concrete production also accounts for a striking share of global carbon emissions, largely from the intense heat required to manufacture cement. It cost the Romans, quarrying volcanic ash instead of burning limestone at industrial temperatures, never had to pay. So the next time you cross a bridge without thinking about it, or walk across a sidewalk cracked with weeds pushing through the seams, or stand under the dome of a building whose ceiling curves without a single visible support, you are standing inside the longest-running experiment in material science that human beings have ever conducted. One that started with volcanic ash near a Roman harbor, nearly ended a career and hundreds of lives in a California canyon in 1928, and is still, quietly, being rewritten today by scientists studying 2,000-year-old concrete cores under a microscope. What stays with you, in the end, is not really the collapse itself, dramatic as it was. It is the shape of the mistake underneath it, a mistake made not out of carelessness, but out of trusting a young material as if it were an old one. The Romans built with a formula refined by trial and coastal weather over centuries, and simply let time do the rest. The modern world built with a formula barely 100 years old, applied with industrial confidence to structures meant to hold back rivers and hold up cities, without yet understanding everything happening chemically inside the mix. Concrete, it turns out, keeps a kind of memory of its own recipe, heals when it was built to heal, and slowly fails when it was not, no matter how much steel or ambition gets poured in with it. So here's the question, worth sitting with the next time you walk past a construction site, watching wet gray concrete being poured into wooden forms. Are we still making the same mistake the engineers of 1928 made, trusting a young material to behave like an old one, somewhere in the infrastructure being built around you right now? And if a 2,000-year-old Roman harbor wall can outlast a 20th century American dam, what does that tell us about how much we still don't know about the ordinary materials holding up the modern world? Main sources for this story include the official 1928 California State Inquest testimony and subsequent engineering reviews of the St. Scene. Francis Dam Disaster, Vitruvius's De Architectura, Marie Jackson's 2017 research, published in American Mineralogist on ancient Roman marine concrete, and research from Delft University of Technology on bio-based self-healing concrete. The full list is in the description.